Hi, everybody. Welcome to the session. So, you're in for a treat. We have Denali Lumma, and she is here to talk about something amazing. So, just a quick background about Denali. She and I actually go way back. She used to speak at Selenium Conf and be very active in test automation and end-to-end testing. And she's got a huge background where she's now a technology executive, more than 20 years of experience in startups to IPO companies, small, mid-sized, global companies, you name it. She's worked at all shapes and sizes of companies. She's helped to build multiple unicorns, my favorite animal, and my daughter's favorite animal, as an early engineer at companies like Netflix, 23andMe, Okta, Salesforce, and Uber. She's a superstar. She's amazing. And so she's here to talk about something amazing that I think we all need to listen to. So I'll leave it to Denali to take it from here.
Thank you so much, Dave. That's very humbling introduction, but I'm really happy to be here and see everyone in the test automation community. I am going to go ahead and present the screen, and I hope everyone can see that. So yeah, a big part of people who focus on test automation, build automation, release automation, all of the things that go into the software development lifecycle, I think is this concept that we use, this phrase that we use frequently called technical debt. And I wanted to sort of dive into this idea with you all today. So Dave shared my background. And yep, have done a lot of work in a lot of different spaces, quality, release, DevOps, just software development in general. And kind of fell in love with the problem, 20 years ago, and never really stopped loving the problem of essentially, at the end of the day, helping people to build technology that is valuable and successful. So if there's one thing that you take away from this talk today, here it is, just for clarity, which is I have an assertion that I have kind of come upon with research and analysis and looking at data and all of the experience that I've had working with teams over the years. And that is that accurate forecasting of future value of a code base or a company that produces code is actually possible. And there's sort of a key metric that can help with this that I call cycle time variance. So let me go ahead and dive into what that means with kind of describing the agenda. So for the talk today, I'd like to cover sort of the concept of technical debt, the concept of technical capital, which is kind of a new idea that I've been formulating, and then share some of the techniques that are actually used to accurately forecast value in finance that I think can be also applied to accurately forecasting value in technology. I want to cover some kind of concepts in math that might sound a little bit scary, but actually are pretty straightforward. And then finally kind of explain what is cycle time, what is cycle time variance. And then I would actually like to share with you some open source examples of comparison between competing open source projects, for example, PyTorch, TensorFlow in the machine learning framework space, but also databases, browsers, front-end frameworks, and code editors, and actually look at whether or not this theory kind of holds up in terms of open source value and sort of operational execution and operational excellence. So let's start with the tech debt metaphor. So a lot of people say tech debt, oh, we're incurring tech debt, or there's a lot of tech debt. And there's sort of this implication that tech debt is like credit card, sort of consumer credit card debt. And there is a similarity in that tech debt is compounding that we all kind of can experience. But essentially, when we use the term tech debt, we're forecasting the future state of the code base. We're forecasting the future value of the code base. And the idea is that an ounce of prevention is worth a pound of cure, which is a pretty good idea. But tech debt isn't really credit card debt. The metaphor kind of breaks down quickly if you try to go too deep into it. And really what the problem is in terms of software development and teams who are working on software development is a problem of understanding. of humans understanding the software. That's actually the core problem. And when we say tech debt, what we actually mean, in my experience, is actually just the answer to the question of how hard or easy is it to understand the system? How understandable is the system from a new hire, a new person joining the team, or someone who maybe doesn't have sort of that, years of experience with it. And so in a way, I actually think tech debt is more akin to losing your mind than incurring credit card debt. And so tech debt is working with the system that really can't be understood or is very hard to understand. How much tech debt do you have? Well, I think the answer is pretty simple. It's how easy can the system be understood, or how easily can the system be understood? And it turns out that understandability is actually quite easy to measure. And the measurement is how quickly can a change be made? And we refer to this in industry as cycle time. And this is actually the first of 4 key metrics defined by DevOps Research and Assessment, or DORA, that really can point to the health of a code base, the health of a team. Cycle time is basically for the time from when you start working on a change, usually measured by like topic branch creation, to when that change is deployed into production. Or it can also be proxied to when that change lands in main. But essentially, it's the time to make a change. In my opinion, though, more interesting and important than the concept of tech debt is actually something different when it comes to trying to forecast the value of the code base into the future. And I like to refer to this idea as technical capital. In the world of finance, there are lots of metrics that are used to forecast the future value of a company, and I think the same frameworks can be used to forecast the future value of a code base. So let's talk about forecasting a little bit. So forecasting is done with a lot of different techniques, but sort of the fundamental thing that is used all the time is working with time series data and statistics. And it's interesting, this is a conference about AI. I would say a lot of the concepts that AI teams use to kind of build neural networks and decide on categorization and sort of likelihood of certain things really comes from foundationally kind of the field of statistics. And so if you're interested in learning about how AI actually works, I think starting with understanding statistics is a good place to start, actually. But time series data is data that we use often when we're forecasting. And basically, it's pretty simple. There's a value or a set of values that's associated with a timestamp. And so essentially, we can look at how the data changes over time. And this is really important to understand forecasting. We look at sort of change in data over time in the past, and then we can sort of infer or predict what the behavior of the data will happen in the future. So this is some simple example of financial time series data, closing stock price by day. So it's extremely simple. There's a date and there's a closing price for the stock of a publicly traded company. In the realm of technology, in the software development lifecycle, we also make heavy use of time series data, or we can make heavy use of time series data, where we actually look at the cycle time by day of a team or an organization, and we can kind of tell pretty easily, like, are things getting better, are things getting worse, are things staying the same, with kind of the fundamental premise that the faster you can make the change to the code base, the easier it is to understand the code understandability, the better the team is executing. So there's a couple of things to be aware of or to understand just from a math perspective. So one concept is this concept of mean, which is value-based. So when we have sort of a collection of numbers, and this is probably the concept that everyone's most familiar with, we can sort of infer a certain characteristic about that collection of numbers by taking the average. This is the mean, where we sum up all the values and then we divide by the number of values and we get the mean or the average. There's another way of understanding a collection of data, which is called the median, which is different than the mean and important to understand. And this is actually position-based. So essentially what this means is if you take a data set and then you order it like in ascending order, and then you basically find the position that is in the center of that data set, then you have found the median, which is the position that separates the higher half from the lower half of a sorted data set. And so the median actually gives us a way to start to calculate and understand this thing called a percentile. So the median happens to be the 50th percentile, but other percentiles can be calculated, the 25th percentile, the 75th percentile. And this is really important concept to understand if you're working with, for example, DevOps, if you're working with like monitoring system health and you want to see changes. Oftentimes, if you're just taking the mean or the average, a lot of outliers or important things will kind of get lost. And this will give you a way to actually understand the data with more clarity. So all of these ideas kind of contribute to this concept of what we call a Gaussian distribution, which is something that probably kind of the common term that some people might be familiar with is the bell curve. And this is also important because it basically gives us another way to understand a set of data and how that data kind of relates to each other. The Gaussian distribution will sort of tell us the mean and then the data dispersion. So will the curve kind of be short and relatively close together, or will the curve be long and actually spread out across the x-axis? So key properties of a Gaussian distribution, as I mentioned, the mean, which is just the central point of the distribution, and then something called the standard deviation. And essentially what this tells us is how small or how big is the variance between the data, each data point in the data set. And so something with a smaller standard deviation sort of indicates that the data is more close together and centered around the mean. And something with a larger distribution means that the data is more spread out. So sometimes when we're talking about math, it's helpful to have an example and looking at, an actual data set. So let's look at this example data set. So 1, 1, 1, 1, 2, 10, 17. I think we all kind of maybe intuitively know, okay, what's the average or the mean of this data set? Well, we sum it up, we divide by the total number of data points, and we get approximately 5. What is the median? Well, this is a little bit different, right? So we make sure the data is ordered, and then we take the midpoint from a positional perspective, and we see that the median in the data set is actually 1. Well, what is the 75th percentile? Same thing, we order it, we look positionally, and we see the 75th percentile here is actually 10. All right, so what is the standard deviation of the data set? So this is where things get a little bit complicated. Everything else so far we kind of could do in our head, but this we can't actually do in our head. This is too complicated. We need a piece of paper, a calculator, or a program to actually do this. But the high level kind of steps to calculate the standard deviation of the data set is first we find the average, then we subtract the mean from each data point to find the deviation from the mean for each data point. Then we square each of these deviations, then we find the mean of the squared deviations, and then we take the square root of the mean of the squared deviations. So yeah, try doing that in your head. I think it might be a little bit difficult, but here are the steps if you want to kind of see how this works. So calculate the mean, calculate the deviation from the mean for each data point, square each of these deviations, find the mean of the squared deviation, take the square root of the mean of the squared deviations to find the standard deviation. Okay, so in summary, for this data set, we have the mean, which is 5, we have the median, which is 1, we have the 75th percentile, which is 10, and we have a standard deviation, which is 6. There's another set of concepts that are very common and very useful when we're talking about forecasting value in a given system, and this is oftentimes used in finance, but also security. So in statistics, there's something called a t-score that is kind of like a standardized score that can indicate how many standard deviations an individual data point is away from the mean of a distribution. And so we can tell kind of like if this is often used with anomaly detection. So we can say like, okay, this score is actually quite divergent. There's quite a large variance from the data that we're used to seeing here, and is often kind of the fundamental algorithm that's used with security technology. And so here's the formula for calculating the t-score that makes use of the standard deviation and the mean. There's also something called the z-score, but they're very similar. The z-score basically assumes access to the entire data set, and the t-score assumes access to just a sampling. And so with a lot of these technologies, or with these concepts, these math concepts, we can sort of start to understand changes over time, and looking at things like rolling average, trend line, relationship between t-score and z-score, and we can see kind of the behavior of a system based on data that changes over time, or time series data. There's a whole field of math called Ito calculus that is interesting if you want to kind of look into that. And there's also someone who's worked in finance and is sort of considered to be one of the great thinkers in finance, named Harry Markowitz, who came up with a concept of modern portfolio theory, and basically a way of thinking about investing with reduction in risk and sort of increase in return. In short, the summary of his work, the main concept was to reduce variation. The reduction of variation is actually a very common idea across many fields, not just finance, but also manufacturing, quality control, healthcare, construction, all sorts of things. And there's actually a lot of historical thinkers that have been really focused on this idea of the importance of reducing variation. So it actually doesn't matter what the mean is. What is more important is that the process over time is consistent, and there's not a ton of variation in terms of time it takes or value. All right, so my assertion, and based on my experience and the data that I've been analyzing, is that essentially the technical debt of a system can be measured very well with cycle time. And the technical capital of a system, or how likely it is that the system will be worth money in the future, can be measured with cycle time variance. So let's look at some open source examples. Let's start with machine learning frameworks. This is a topic everyone's very interested in right now. And so we look at TensorFlow and PyTorch comparatively. So this is a view of the Google Trends, and this is, in my opinion, a very accurate representation of the value of each of these open source projects, each of these software projects, because it kind of mirrors the open source value of a project is really related to developer interest, developer usage. And this is really a direct signal, kind of showing what that means over time. So from here, you can see that initially TensorFlow was very much in the lead. In fact, it may have even started before PyTorch, but at some point, PyTorch is behind in terms of interest, and what we would say is a proxy for value of the software. But at some point, the lines actually cross, and I think it's sort of not disputed anymore that PyTorch is the clear winner here. So let's take a look at time variance, cycle time variance, and cycle time. So the cycle time is in red and the variance is in blue. And you can see that cycle time is getting faster, which is good. We always actually want cycle time to get faster. But almost like more importantly, the standard deviation of that time is actually pretty consistent. Here's TensorFlow. So actually the inverse, right? You can see cycle time is actually getting longer. So it's taking longer and longer to make a change. In the red line, you can see that over time. But also, more importantly, the variance between the time changes is increasing pretty significantly. This is not good. So we compare PyTorch with TensorFlow. It's a very interesting graph in terms of the standard deviation. PyTorch is going down, TensorFlow is going up. And when I see this, it's like I feel like I'm a character in the Matrix. I don't see graphs anymore. I just see value. You could say that the interest or the proxy for value shift away from TensorFlow toward PyTorch occurred at about the same time the standard deviation cycle time for the two projects crossed. Okay, let's look at databases. MySQL and Postgres. So at one point, MySQL was very much in the lead, and Postgres was not very interesting to most people and didn't have a lot of value. But you could see over time, these are converging. So Postgres, here's a picture of Postgres cycle time and cycle time variance. And here's a picture of MySQL. And just to compare, so Postgres is actually quite steady, quite stable. But MySQL, we see like quite a large shift over time, actually. Variance is increasing, cycle time is increasing. Actually, variance is increasing more than cycle time. And here's how they look compared. And so we could actually say that MySQL's drop in developer interest value appears to be the inverse of their rise in cycle time variance. Okay, a couple more examples, then I'll stop. Browsers, Firefox, Chrome. Firefox was definitely in the lead. At some point, Chrome wins. There's a crossing point. Chrome cycle time variance is increasing. Firefox cycle time variance is also increasing. But when we compare these together, so it's interesting because in this case, the two projects are actually behaving generally in the same way. But you can see that Chrome actually has generally less variance than Firefox, even though they're both trending in the same direction. So the rate of increase of cycle time variance for Chrome and browsers are similar. Chrome is slightly better at a factor of 90, whereas Firefox shows a factor of 99. And Chrome also was significantly below Firefox in terms of variance from a starting perspective. So the theory kind of holds true with this data set as well. Okay, front-end frameworks, Angular, React. These were kind of neck and neck, but at some point, React kind of broke free as kind of the clear leader and dominant successful project. Here's a picture of React. Here's a picture of Angular. So interestingly, cycle time for Angular is going down, but variance is going up. And here they are kind of in comparison. This one is an interesting one. I'm not seeing kind of a clear signal here. And when I first saw this, I was like, there's a glitch in the matrix, like this doesn't make sense to me. But my conclusion, which I think does make sense, is that both Angular and React are moving in the wrong direction with little distinction, and there is room for a third player. So if anyone's interested in creating a new front-end framework, I think there's an opportunity here. Code editors, and then we'll conclude Emacs, Vim, and VS Code. So Emacs was definitely in the lead, but they converge with Vim, and then at some point VS Code takes over. And this pains me because I'm an Emacs person, but that's okay. VS Code cycle time and variance is here. Vim cycle time and variance, and Emacs cycle time and variance. And we can see these sort of compared. So Emacs is definitely kind of performing the worst. And Vim and VS Code are very similar, actually. But VS Code does have a slightly lower rate of growth at 58 than Vim at 61, essentially. And although Vim did start at kind of a lower technical debt point, crossing the y-axis. But in general, this is what I would expect. So the leader in the market, VS Code, has the lowest variance trending, and the second most popular Vim has the second lowest variance trending. So in conclusion, I believe that this kind of insight can be very useful for people who work in technology, who work with as quality professionals, as technical professionals. there's often a situation where venture capitalists are trying to value a technology company and they make kind of the wrong call. This is a technique and approach that could actually offer some data-driven valuation with cycle time valuation, and kind of help to determine whether or not it's a good idea to invest in a business, sort of favoring investment in businesses with lower cycle time variance. Another situation where I think this could be useful is as a technology operator. You're facing a lot of different problems, technology problems, communication problems, visibility, vendor and partner, supply chain, all sorts of things. And it can be difficult to know sort of how things are going. And I think this approach can really help technology operators and just company operators understand how things are going from a future value of the code base perspective by looking at cycle time variance. And that's it. Thank you so much. I will try to stop sharing my screen now. All right.
Hello, cool. Well, first of all, I didn't know you're an Emacs user, and I didn't know that we can't be friends anymore because I use Vim. So that's unfortunate. Thank you for a great talk. Just a couple of quick bits of housekeeping before we dive into Q&A. For everyone here, please do submit feedback. It's in the chat area. There's a puzzle piece icon. So the puzzle piece, go and search for that, and be sure to fill it out. It makes us have a better show and improve for next time. And then also, Richard does want to see there's a call to action at the bottom of the window. Richard wants to hear about your fears about the use of AI in testing. So answer the poll before his session, the fear factor. Enough clickbait. What else? Last thing is just if you're looking to, if you're overwhelmed by the math and you want to get back to some test automation, there is a guide focusing on modern test automation. It's in the resources tab. So be sure to check that out before you leave if you're interested in that. Cool. Now, on to the questions. We had a lot of great interest in the talk. So we'll try to get through a couple questions here. Can you share any real world cases where the conversion of technical debt to technical capital led to cost savings or improved product quality?
Well, I do actually have some examples. I have some case studies. I think they're posted on my website. So I am doing a couple of different things right now. So I have a couple of years ago started a kind of boutique consultancy, just working with investment groups like Y Combinator and Andreessen Horowitz and other groups, sort of advising, doing essentially what's referred to as like fractional CTO, interim CTO, or just technical advisory work. And a lot of the times when I sort of got called in to do this or get called in to do this, it's really for like teams that are really in trouble, that are having serious problems with quality, serious problems with velocity, that have oftentimes missed their roadmap timeline, targets by like 6 months, 12 months, 18 months. So I do have case studies of kind of technical turnarounds, and usually we're able to improve velocity by about 10x and quality by about 2x in about 90 days. And we start that process by doing a baseline and just measuring. So let's measure like the velocity, let's measure the quality with the DORA metrics, the 4 key metrics: cycle time, deployment rate, change failure percentage, mean time to resolution. We also started open sourcing the Python code that we use to run Git analytics on a repo. So you're welcome to check that out on GitHub. And there's a lot of vendors out there that do this, but most of them require like GitHub as the provider and sort of a very excessive like authorization. So we came up with a tool that can give you these insights that just can run on a local repo. So feel free to check that out or reach out to me as well. I'd love to share the case studies.
Got it. Okay, just to dovetail into that, there was a question that ties in, and I think you partially answered it, but it was, how do you stop teams from increasing their cycle times at the expense of quality in order to be better and the quality delay problems? So how is that incorporated into this?
Great question. I love that question. So in the deck that will be shared, the presentation was supposed to be 20 minutes, but the deck itself is like more than 100 slides long because there's a huge appendix section. So I was trying to explain this to Dave, so I didn't scare him beforehand.
I was a little scared.
But in the deck, there's a whole section in the appendix on this topic. So the interesting thing is, from research that we know from DORA research, it turns out that a lot of people think that there's a trade-off between cycle time and change failure percentage, but they actually move in tandem. So it turns out that like teams, and I've been doing this for so long, I just, it's like, and the numbers are so correlated. Like if I know one number, I pretty much know the other 4 numbers, more or less. So teams that have a really low cycle time, like for example, half a day, 4 hours, 8 hours, also almost always have a super low change failure percentage. So like 10% or less in terms of rework, where the change failure percentage is like of the total number of changes made in a given time frame, like a week, what percentage of those are hot fix, bug fix, or revert? In other words, what percentage of those are rework? And this metric will tell you very clearly the quality of the code base. And usually these two things actually move in tandem. So the longer the cycle time, the higher the change failure rate. The lower the cycle time, the lower the change failure rate. So oftentimes when we start working with teams, like teams I've worked with in a really bad situation where they have like a 365-day cycle time to land a change, you can imagine how that team would work, right? It's like, we're going to build something, it's going to be amazing. The first time you're going to see anything is a year from now.
Wow.
We know intuitively like that won't work, right? We know intuitively it's going to be late, there's going to be tons of bugs, it's probably not, what the users even want. So we want to reduce that time down by breaking things up and decomposing into smaller features. But another really important thing is code coverage, unit testing, test automation, and starting to introduce that into the code base as well. So that's often how we start, is like, okay, let's decompose these issues, and then let's do some very lightweight testing, maybe just with unit tests to start with.
Okay, awesome. Amazing answer to the question. Thank you so much. This was a super informative and for me, very interesting session. And I didn't know that you have this sixth sense for just, you see it like the Matrix. And so that's amazing. So very cool. Thank you, everybody, for joining. Thanks for the questions. Thanks for the engagement. And Denali, thank you so much. Everyone, we'll see you in the next session.